lesson, we're going to talk about scientific notation. Today we're going to learn how to read and write numbers in scientific notation. Scientific notation is a shorthand way of writing numbers using powers of 10. The key concept of scientific notation is a number written in scientific notation if it has the form of C times 10 to the nth power, where C is greater than or equal to 1 and less than 10, and n is an integer. So C needs to be a digit. It can be 1 or greater than 1, but less than 10. In some examples, in standard form. In standard form, we have 2,860,000. The product form is listed, but most importantly, what we're going to go over today and in this lesson is the scientific notation. The scientific notation of that number would be 2.86 times 10 to the 6th power. Again, as in the form of the example previous, the C part is 2.86. It is going to be either equal to or greater than 1, but less than 10. And the 10th, the power, its power is an integer. In the next example, in blue, it is 600 thousandths. It is a small number, so notice the difference in the power. It is a negative power. The powers indicate how many places or place values you're going to move the decimal. So we're going to have a word problem using scientific notation. The retina is a layer of the eyeball that contains rods and cones. Rods and cones are cells that absorb light and change it to electric signals that are sent to the brain. The human retina is about 0.00012 meter thick and contains about 120 million rods and about 6 million cones. Now we're going to take two of these numbers and change them from standard form to scientific notation. Let's take the larger number in standard form. Now we're going to change 120 million to scientific notation. Remembering the rule for that, the first part has got to be greater than or equal to 1 and less than 10. And then you're going to denote how many times you need to move the decimal in order to get 120 million. So in this example, we're going to move the decimal point 8 places to the left to put it in scientific notation. It is a large number, so your exponent in the power of 10 is going to be a positive. It will be an 8. Let's put the next example in standard form. Again, in order to put it in scientific notation, we need to determine if the exponent is going to be a positive or a negative. So in order to determine what our exponent will be, we need to see how many places we need to move the decimal in order to put it back in standard form. We will be moving it to the left 4 places. So your exponent for the small number will be -4. Now let's notice when we're dealing with powers of 10, when we're dealing with powers of 10, again, it denotes how many times you move the decimal place. So 10 to the first power is going to be 10. 10 to the second power is 100. So when you're having a power, it actually denotes how many zeros you will have. Catch up. So again, each of them denotes the place value that you're going to be moving the decimal. In this next word problem, now Eiffel Tower has about 6,300 metric tons of iron. Write 6,300 in scientific notation. So that in scientific notation would be 6.3 times 10 to the third, because we need to set it up the first part to be less than 10, greater than or equal to 1. And how many places do you need to move the decimal in order to get 6,300? And it was 3 times to the right. Now, I've given you guided practice for A, B, C, and D. I'm going to pause the video and we'll come back and check our answer. Okay, notice that on each one, we determined what type of number it was. It was just a large number, and it's going to have a positive exponent. That's an easy way to check it. If it's a small number, it will have a negative exponent, because that's the direction that you move the decimal. And how many decimal places that you move, or how many place values that you move the decimal, indicates what the power is. Okay, so in our next section, you're asked to write the number in standard form. I'm going to pause the video, come back and check your work. Okay, so in the standard form, the first one will be 7,000, 7,000. B, 439, 800, 000. C, 0.0000103. And the final one will be 0.0983. In our next example, we're going to be asked to compare certain numbers in standard form. Mars has 2 moons, Phobos and Deimos. Phobos has a mass of 1.06 times 10 to the 16th. Deimos has a mass of 2.4 times 10 to the 15th kilograms. Which moon has the greater mass? Now, when you're asked to compare numbers in scientific notation, the solution is to compare the numbers written in scientific notation. First, compare the exponents. So we're going to look at the exponents first. Then, if the exponents are the same, you compare the decimal points. First of all, make sure that they are in scientific notation before you go any further. Both of these numbers are in scientific notation. So noticing that comparing the exponents first, they're both in scientific notation. So if you were to determine less than or greater than or equal to, Phobos is going to be larger than Deimos, because 16 is greater than 15. Now, you have 2 examples here. You are asked to order them from ordering numbers using scientific notation. You're going to order them from least to greatest. Notice you need to put one of them in scientific notation, then put them back in the original format, going from least to greatest. I'm going to pause the video. We'll do the first one, and I'll come back and check. Okay, notice that we put 3,800,000 in scientific notation. 3.8 times 10 to the 6th. Then, in order from making sure they're all in scientific notation, and they are, we're going to put them in order from least to greatest, first by looking at their exponents. So notice that has a 6, that has a 6, and that has a 5. So our smallest one is going to be 4.2 times 10 to the 5th. Then we're going to compare the 2 that have the same exponent by their decimals, 3.9 and 3.8. So we order them in their original format, and that is your final answer. Notice that we put 8,700 in scientific notation, compared it to the other powers. We had 2 that had the same power, so then we compare the decimals. put them in order from least to greatest in their original format. All right, now we are going to multiply numbers in scientific notation. In our example, we're talking about a Wolffia plant, and it is the smallest flowering plant in the world. In the picture here, there are examples of the Wolffia plant in a thimble. One Wolffia plant has the mass of 1.5 times 10 to the negative fourth power. At least 5 times 10 to the third plants could fit in a thimble. What is the mass of 5 times 10 to the third Wolffia plants? So instead of saying it has a mass of, 5,000, they put the mass in scientific notation. So they're asking the question, what is the total mass of this example here? Let's set this up. The question is being asked, what is their total mass? In order to find their total mass, you're going to take the mass of one plant and you're going to multiply it times the number of plants. Now, so the total mass, the mass of one plant times the number of plants. So in order to find the total mass, we took the mass of one plant, multiplied it times the number of plants that were given in the example. And because of commutative property of multiplication, we can pick any two to multiply. So we chose 1.5, multiplied it times 5, which is 7.5. Then we took our powers of 10, and multiplied them. And as you can remember, when you're multiplying powers of 10, you actually add them. So negative 4 plus 3 is negative 1. So now we have 7.5 times 10 to the negative 1. That in standard form is 75 hundredths grams. In our next word problem, we have a nickel has a mass of about 5.2 grams. What would be the mass in grams of $1,000 worth of nickels? So in this example, we had a very large problem that we needed to solve, but we decided to break it down into a simpler problem. We needed to find out what the mass was of the amount of nickels in $1,000. So the first thing we decided was, what is the mass of nickels in $1? Or how many nickels are in $1? So there's 20 nickels in $1. So if there's 20 nickels in $1, we take 20 and we're going to multiply it times 1,000, which gives us 20,000 nickels in $1,000. So if each one of those nickels weighs 5.2, we change that $20,000 to scientific notation, then multiply using the commutative property 5.2 times 2, and we got 10.4, and brought down our power of 10.4. But our final answer needed to be in scientific notation, so we moved the decimal to the left and changed the exponent to 5. Here we go. In our last example, by what value would you multiply 6.2 times 10 to the negative 2 in order to obtain 6.2 times 10 to the second as a product? Think about place values. Your answer, you're starting off with 6.2 times 10 to the negative 2. You're going to take that number and you're going to have to multiply it times something in order to obtain 6.2 times 10 to the second as the product. Again, the powers are dealing with decimal places. So your answer will be a 10 to a certain power. So your answer will be, in order to have the product of 6.2 times 10 to the second, you'll multiply it times 10 to the fourth, because you would have been moving the decimal 4 places.